Okay, so imagine you're watching the fastest runner you know. I mean, they're just a blur, right?
Right, incredibly fast.
Now imagine they could run so fast that, I don't know, their water bottle literally looks squashed
Mm.
and their stopwatch. It starts ticking slower than yours. And no matter how fast they run, they just can't break this, like, ultimate speed limit.
That's not science fiction. That's the universe that Albert Einstein showed us back in 1905. It's this world where your speed, well, changes everything.
And that's what we're doing today. We are diving deep into the original paper itself, a work called On the Electrodynamics of Moving Bodies.
It sounds a little heavy, I know. But the core ideas are actually, I mean, they're really mind-bending and fun.
So our mission here is to be your guides. We want to show you how movement literally changes the things we think are fixed. You know, time, distance.
And speed itself. You'll see why the universe actually bends around you when you start moving really, really fast.
And here's where it all started. This is what I find so interesting. Einstein wasn't trying to mess with time. He was solving a really specific puzzle.
Exactly. A puzzle about magnets and electricity. The paper opens by pointing out this weird unfairness and asymmetry in how physicists were explaining things.
What do you mean by asymmetry?
Okay, so imagine you have a magnet and a coil of wire. If you move the magnet toward the wire, you get an electric current.
Okay, simple enough. Motion creates electricity.
Right. But if you hold the magnet still and move the wire toward it,
You'd get the same thing, right? The same current.
the exact same current, the result is identical. But the old physics had two totally different explanations for why.
Wait, why? If the outcome is the same.
That was the big question. In one case, they'd say a magnetic field was the cause. In the other, they'd say an electrical force was the cause. Einstein looked at this and basically said, hang on, this distinction does not appear to be inherent in the phenomena.
So he's saying the universe shouldn't care which thing is moving.
It only cares that they're moving relative to each other.
That's the big aha moment then.
It's the moment that kicks off all of modern physics. It leads to this fundamental question. What if there's no such thing as absolute rest? What if everything is just moving relative to everything else?
So to build this whole new idea of the universe, he had to lay down some ground rules.
Two of them, right?
Two non-negotiable rules. The two big rules of the universe. And they sound simple, but if you accept them, everything else has to change.
So what's the first one? You said it's about fairness.
That's a great way to put it. Rule 1 is the principle of relativity. It just means that if you're standing still, or if you're on a perfectly smooth train moving at a steady speed, the laws of physics are the same for you.
So if I'm on a train and I drop a ball, it just falls straight down.
Just like it would if you were standing on the platform.
Hmm.
You can't do any experiment inside that train car to prove you're moving. All steady motion is equal.
Okay, that seems reasonable. What's rule number 2? Rule 2 is the shocker. It's the one that forces everything else to bend. We can call it. Light is the champion speeder.
Meaning it's the fastest thing there is.
Not just that. It means light always travels at the exact same speed, which we call cedo, no matter what.
No matter what.
No matter what. So if you're standing still and you shine a flashlight, the light zips away at speed, cedo dollars.
Right.
But, and here's the part that makes no sense. If you're in a rocket moving at half the speed of light and you shine that same flashlight forward.
And it should go at 1.5 times the speed of light.
Yeah.
Right? Your speed plus the light speed.
It should, but it doesn't. It still just moves away from you at speed.
Wait, how is that possible? I mean, everything else adds up.
Because light is special, it's a universal constant, and Einstein realized that for Rule 1 and Rule 2 to both be true at the same time.
Well, the only things that could give are our ideas of time and distance.
Time and distance are flexible.
They have to be. Okay, my head is already spinning.
Yeah.
Let's dive into that, because this is where reality really starts to get weird. We need to talk about what at the same time even means.
It's a concept called simultaneity. We think it's simple. You know, if a bell rings across town right as your watch hits 7:00, they happen at the same time.
Sure.
But that definition only really works if you're standing still.
So how did Einstein define it?
He used light, of course, the one constant thing. He imagined two clocks, A and B, really far apart. To synchronize them, you send a flash of light from A to B and have it bounce right back.
Okay.
He said they are only synchronized if the time it takes the light to go from A to B is the exact same as the time it takes to go from B back to A.
That's clever. He's using light as the ultimate measuring stick for time.
But it leads to a truly shocking result. We call it the relativity of simultaneity.
Which means?
It means that if you're standing still and you see two lightning bolts strike at the exact same time, they're simultaneous for you. But for your friend who is flying past on a super fast train, she would see those two bolts strike at different moments.
What? So they're not simultaneous for her. The moment itself depends on who's watching.
Exactly. Your speed changes your perception of when things happen, and that leads directly to the most famous part of all this, time dilation.
The moving clock mystery. The idea that moving clocks run slow.
That's it. Let's say we have two perfect clocks. We synchronize them side by side. Then you take one on a very fast trip around the world.
And I bring it back.
When you put it next to the clock that stayed still, yours, the one that moved, will be lagging behind. It will show that less time has passed.
So I would be younger, technically.
In a way, yes. The faster you move, the slower time ticks for you relative to someone who is stationary. The moving clock is a slowpoke.
And this isn't just a theory, right? This is real.
Oh, it's very real. The source paper even brings this down to Earth, literally. It points out that because the Earth is spinning, a clock at the equator is moving faster than a clock at the North Pole.
Because it has a bigger circle to travel every day.
Right. And because of that extra speed, the clock at the equator must run just a tiny, tiny bit slower than the one at the pole.
Wow. So motion is changing time, all around us, all the time.
Yes.
Okay, so if time is flexible, space has to be too. Distance must change. Let's talk about these incredible shrinking objects.
Yes, let's move from time to length. Imagine a simple ruler. You measure it when it's still, and it has a certain length. We'll call it dollars.
My ruler is a foot long, length dollar.
Perfect. Now, what happens if that ruler is moving past you at an incredible speed?
Well, if I'm holding it, it's still a foot long to me. Rule number one, right?
Yeah.
The laws of physics are the same in my little world.
Exactly. For you, the person moving with it, nothing changes. But what about for me, the person standing still watching it fly by?
I guess you'd have to measure it somehow.
And to do that, I have to know where the front end and the back end are at the exact same time in my system.
But we just learned that same time is tricky.
It's very tricky, and when you do the math, you find something amazing. The length that I measure is different. It's shorter.
It shrinks. That's length contraction.
That's it. And it only shrinks in the direction it's moving.
So if it's flying past me horizontally, it gets shorter, but it stays the same height.
You've got it. The source gives a great way to picture this. Imagine a perfectly round ball, a sphere.
Okay, like a soccer ball.
Now, you start moving that ball very, very fast. To someone standing still, it won't look like a sphere anymore. It will look squished.
Squished in the direction it's moving, so it would look like a flattened A.
Precisely. It becomes what's called an ellipsoid of revolution, a squashed ball. The faster it goes, the more squashed it gets.
So what's the limit? What's the ultimate squish?
Well, if an object could somehow reach the speed of light, the math says its length and the direction of motion would shrink all the way to zero.
To zero.
The paper says it would shrivel up into a plane figure.
Like a pancake.
Mm-hmm.
A completely flat two-dimensional slice. That is just so hard to get your head around. But it brings us to the final big question. If all this weird stuff is happening, why can't we just push harder and go faster than light? Why are we hitting the speed wall?
We know from Rule 2 that light speed is the limit. But this is the why. Because in the old physics, speeds just added up.
Right, the car and the ball example. 60 plus 30 is 90. Simple.
But relativity gives us a new, more complicated formula for adding speeds. And the punchline is, if you combine any two speeds that are less than $70, say a rocket going at 90% the speed of light launches another rocket at 90% the speed of light.
You'd think that would break the barrier.
You would. But the math shows the result is always still less than c to vol. You can get closer and closer, but you can never quite reach it.
The universe has a built-in safety brake.
It does. Even if you try to add a speed to light itself, the answer is still just $2. Light speed can't be altered. But the deepest reason you can't push past it has to do with mass.
Mass meaning how heavy something is, how hard it is to push.
That's a great way to think of it. It's an object's resistance to being accelerated. Now think about the energy it takes to push a tiny particle, like an electron, faster and faster.
Okay, give it a push, it gets more energy, it goes faster.
Right. But as its speed gets closer and closer to the speed of light, something amazing happens. Its effective mass starts to increase.
It gets heavier.
It gets infinitely harder to push.
Yeah.
As its velocity gets closer to $2, the energy required to make it go even a tiny bit faster starts to approach infinity.
Infinite energy. But there isn't infinite energy.
Exactly. To get that particle all the way to the speed of light would take all the energy in the entire universe.
Yeah.
And so the theory proves that, quote, velocities greater than that of light have no possibility of existence.
It's the ultimate wall, because the
Mm.
object basically becomes infinitely massive.
You got it.
So it all connects. The moving clock slows, the moving ruler shrinks, and the moving object gets infinitely heavy.
So what does this all really mean? Einstein's paper completely changed our picture of reality. It showed us that these things we thought were solid and absolute time, length, even mass, are actually flexible. They depend on your state of motion.
Your view of the universe literally depends on how fast you're going.
Yeah.
It's not a fixed stage where things happen. The stage itself stretches and shrinks with you.
And to leave you with a final thought, something else that comes directly from this source. We know light speed is fixed, but the theory also predicts that if you, the observer, were approaching a light source at the speed of light,
Which we can't do, but theoretically.
right, theoretically, that light source would appear to have infinite intensity.
It would be infinitely bright, just because of how you're moving relative to it.
Yes, a kind of ultimate Doppler effect. So if just changing your speed can make a normal light bulb seem infinitely bright, what other incredible secrets are hidden in our world waiting to be revealed just by changing how we move through it?
Something to think about. Thank you for joining us for the deep dive.